Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's Scribblecast of organic chemistry lectures and solutions to homework problems. In this Scribblecast lecture, we are continuing with our investigation of carbohydrates. Last Scribblecast lecture, we looked at the molecule glucose. We determined that, unlike the information conveyed in the Fischer projection, that the molecule can actually flex and bend. It can adopt conformations such as drawn here. And this leads the hydroxyl groups to come in close proximity to the carbonyl. We also examined hemiacetal and acetal chemistry last lecture and learned that alcohols can react with aldehydes to form hemiacetals. Well, glucose has its own hydroxyl groups, and hence the alcohol groups can react intramolecularly to form cyclic rings with ether-like linkages. When the OH actually attacks the carbonyl, this will produce a hydroxyl group, and it will yield a new chiral center. Because of this, the hydroxyl located at this chiral center could be pointing up or down. So when the hemiacetal forms, it creates a new chiral center with both possible stereochemistries. Now, what evidence is there that this actually occurs? Well, for the molecule D-glucose, D-glucose, when dissolved in aqueous solution, behaves as if it has 5 chiral centers, not 4. This is strong evidence that indeed the molecule does undergo a cyclization process, such as shown here. Now, one of the problems we have is how are we going to designate this D-glucose molecule? That is, if the open chain Fischers call D-glucose, what do we call the ring structures? Well, the ring structures are named based on their close relationship to this molecule structurally. Although this molecule has double bonds, it does have a 6-membered ring in which one of the atoms is oxygen. This molecule's common name is pyrane. Since we are dealing with sugars, the O ending is added, and both of these molecules are referred to, when you have the ring structure, as D-glucopyranose. So when you have a straight chain Fischer, you have D-glucose. But when you have the sugar in a ring structure that is a 6-membered ring with one of the atoms being oxygen, you have a pyranose ring, and hence we have, in the case of glucose, D-glucopyranose. Now clearly we need a way of distinguishing between these two D-glucopyranoses. And we need to determine some ways of referencing the carbon that has become chiral upon cyclization. Now, the carbon that is chiral during the cyclization process, that becomes chiral, is referred to as the anomeric carbon. So the anomeric carbon is the carbon that was the carbonyl carbon, but now has become chiral upon cyclization. It is the carbon whose chirality produces 2 different stereoisomers when you form the pyranose ring. The relationship between the 2 D-glucopyranoses, since they are not mirror images and are non-superimposable, is that they are diastereomers. So these 2 molecules are diastereomers. More than that, these 2 diastereomers differ in chirality at only 1 chiral center. Hence, they are also epimers. Lastly, you should note that the chirality differs at the anomeric carbon only. Hence, a special type of epimer is the anomer. They are anomers of each other. Anomers are epimers that differ in chirality at the anomeric carbon only. Now, in order to distinguish between the two stereoisomers, we're going to use the Greek letters alpha and beta. Alpha will refer to the anomeric hydroxyl group on the same side as the reference group. So if the hydroxyl is on the same side, it is called alpha. And so this would be alpha-D-glucopyranose. If the hydroxyl is on the side opposite the reference OH, the one that determines whether it's D or L, it is referred to as beta. Now this cyclization, although I've drawn it this way, can be drawn in a Fischer projection. And we'll come back to these types of ring structures, but what we're going to do is we're going to draw our structures. In fact, let's go complete. And what we're going to do is we're going to draw our glucose, and the hydroxyl that reacted was this one. So I'm going to bring that oxygen all the way around like this. Now, this chiral center can point in one of two ways. Or it can point in the other manner. And this is drawing the previous ring structures I had drawn as Fischer projections. So let's just draw the free Fischer here. Now this is D-glucose. And where is the reference carbon that determines the D? Well, clearly that's this carbon right here. And what a rule about alpha-beta states is that if the OH that becomes chiral, so the carbonyl turns into this OH right here, or this one. That was the C double bond O, but cyclization turns in the OH. If the OH is on the same side as the reference OH, it is alpha. So what we have here is alpha-D-glucopyranose. What we have over here is beta-D-glucopyranose. Now it turns out that these species are in equilibrium. When D-glucose is dissolved. It turns out that the D-glucose in solution, the free straight chain form, is less than 0.02%. And that beta-D-glucopyranose makes up 64% of the solution, and the other 36% is alpha-D-glucopyranose. Now the fact that the percentage is not 50-50 needs or begs some explanation, but before we go there, we really need to learn how alpha and beta relates to the ring structures I drew, and why I indicated which one was alpha and which one was beta. Now the type of drawing that I drew for the ring structures, these are Fischer projections. But the type of drawing that I had drawn was based on a six-membered ring in which there was an oxygen in this position. This is called a Haworth diagram, or a Haworth projection formula. Now the Haworth projection formula puts the oxygen in the upper right vertex, and this right vertex here is my anomeric carbon. This is the standard method of drawing a Haworth projection formula. Now the anomeric carbon is the carbon that was the carbonyl. It's carbon 1. So we number this way around the ring. 1, 2, 3, 4, 5, and so on. Now the question is, how does this structure form from the Fischer? And we have several rules for that. For a D sugar, groups on the right side of the projection are placed below the plane of the ring, and groups on the left side are placed above the plane of the ring. So if I were to draw a ring structure for beta-D-glucopyranose, I can translate the Fischer very easily into the proper Haworth. Left on the Fischer is above. Right is below. Left is above. Right is below. Now for a D sugar, the terminal CH2OH is placed above the plane of the ring. And you can see that for a D sugar, the beta anomer, the OH of the anomeric carbon, is up or above the plane. Now if I draw the same structure for the alpha anomer, it is exactly the same thing, except the OH at the anomeric carbon is now below the plane of the ring. So, this OH right here is on the right, so it's below. The OH below it is on the right, so it's below. OH is on the left, above. OH on the right, below, and then a D sugar, CH2OH. There we go. And there's the Haworth projection formula for alpha-D-glucopyranose. Now, one could take this methodology for drawing these sugars and identify or name the structure. And this can be quite deceiving. For example, let's take a look at beta-D-glucopyranose. If I memorize my sugars, I might say this looks an awful lot like the alternating OH, 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 OH of idose, D-idose. And if I was just to simply use this and call it D-idose, I would be mistaken, because this is not the OH of the Fischer of D-idose, but this is actually the carbonyl. It's the anomeric carbon. Let's try naming a sugar, and we'll do this and come back to the behavior of these Haworths and Fischers. Let's suppose you're given the following random Haworth. So, and you're asked to name this thing. You can see the problem that immediately arises. This is no way similar to the sugars, the list of sugars or monosaccharides, carbohydrates that you've memorized. What do? Well, you use the rules I just gave you to convert this to the Fischer. Okay, so I'm going to convert this to the Fischer. And you start with the anomeric carbon. Remember, above the plane was to the right. Above the plane, above the plane's to the right. Right is below, left is above. Above the plane's to the left. Above the plane's to the left. Below the plane's to the right. Below the plane's to the right. Okay. Now we have this oxygen of the ring that cyclizes. It's D. This is a D sugar, so it's to the right. And if you stop here, you immediately jump to the conclusion that this is D-mannose, because we have two OHs on the right and OHs on the left. Two OHs on the left and two OHs on the right. However, that would be erroneous, because this chiral center right here, this is the anomeric carbon. It's a C double bond O. Before cyclization, that was my C double bond O. So when I draw the Fischer to figure out what I've got, I have an OH here. Okay. And then I have an OH, an OH, an OH. Now let's follow that. Okay, so here is carbon 1. That's carbon 1. Here's carbon 2. That's carbon 2. Here's carbon 3. That's carbon 3. Here's carbon 4. That's carbon 4. And the carbon of the ring, the cyclized, was this one, carbon 5. And then I have the CH2OH. So here's my Fischer of my sugar. What sugar is that? It's not mannose. It's not the 2 on one side, 2 on the other. This is the one referred to as D-altrose. And when altrose, like glucose, okay, is put in a 6-membered ring, it's referred to as D-altropyranose. Now, if this is D-altropyranose, the question is alpha or beta? Remember, alpha has the OH at the anomeric carbon, carbon 1, on the same side as the reference. Well, this one's on the opposite, so it's beta. So you notice I determined the name of this odd Haworth projection by converting it to a cyclic Fischer and then an open chain Fischer. And I do this on scrap paper to figure out how to name it. All right. What about L sugars? Well, L sugars have essentially the same features. If I start with an L sugar and I want to draw the Haworth of it, so let's do L-glucose. So here's L-glucose. I can cyclize. You notice to be an L sugar, now the cyclic O that cyclizes is on the other side. So I've got this guy coming up, going this way. Carbon 1, okay, and let's make it beta. So the OH points opposite the reference, so that OH must point to this side. And now I can put in this OH right here is this guy. I'll asterisk it. Notice that. This OH is the OH of the anomeric carbon. So I continue now with my regular pattern. There we go. And so the Haworth formula for an L sugar, do the same rules apply? Well, not quite. Right is still below and left is still above. So right is below, left is above. Right is below, left is above. But for an L sugar, the terminal CH2OH is down. Notice that applies when the oxygen is in the upper right vertex and the anomeric carbon's here. So if those two positions are not changed, the rule is the CH2OH is down. So when you're drawn. And that's different from the D sugar. Notice also that this guy, the OH here, is opposite the reference here. So this is beta. This is beta-L-glucopyranose. Now, in a D sugar, beta was up. But notice in an L sugar, beta is down. To be opposite the reference oxygen, the OH has to be down. Okay? So beta is down and alpha is up for an L sugar. And that's reversed in a D sugar. In a D sugar, the alpha is down and the beta is up. So your rules for drawing Haworth formulas are given in your handout notes are as follows. For a D sugar, groups on the right side of the Fischer projection are placed below the plane of the ring. Groups on the left side of the Fischer projection are placed above the plane of the ring. The terminal CH2OH groups are placed above the plane of the ring. The alpha anomer, the OH of the anomeric carbon, is down, and the beta anomer, the OH of the anomeric carbon, is up, and that's for a D sugar. Filling it in for the L sugar groups on the right side of the Fischer projection are still placed below the plane of the ring. Groups on the left side of the Fischer projection are placed above the plane of the ring. Terminal CH2OH groups now are down below the plane of the ring. And alpha anomers are above the plane of the ring, or up. And the beta anomer, the OH on the anomeric carbon, is down. All right. Now, having established the drawing of Haworths, we can now use this and generate the chair conformer. And chair conformers can be tricky. So, we're going to go back to D-glucose. OH down, this will be alpha. So what I'm drawing here is the Haworth projection of D-glucopyranose, and I've drawn the alpha anomer. So this is alpha-D-glucopyranose. What I want to do now is convert this Haworth projection into a chair conformer. And I can do that very easily. I can draw a standard chair. And I'm going to put in, so my axials, there's an H here, there's an OH here, OH, OH, CH2OH, and now put in my equatorials. This guy was down, so it's OH. There's that H. Now, how did I know to put the OHs where they are and the H's where they are? Well, you'll notice if I look at this OH is down. When these two are pointed up, you have an axial and that. Which of those two bonds is down? Well, that must be the OH. Come to this guy's down. Well, you have an equatorial and an axial down. So the OH must be in this position. I can draw the ring flip structure by just tilting the central two bonds in the opposite direction. If I do that, I get this type of structure. And if I put in my bonds, I now can put in the groups. You can tell that this OH would now be down. This OH would be equatorial. This OH would be equatorial. This OH would be equatorial. And the CH2OH would be equatorial. Okay. Now here's a question. Both chair conformers, ring flipped A and B, can exist. But what is the most stable chair conformer? Well, if you recall from last semester, the most stable chair conformer is the one that puts the largest groups in the equatorial position. This is where you get the least amount of steric hindrance. The molecules that do this in this case, or the structural conformer that does it in this case, is structure B. You notice in structure B, only one of the OH large groups ends up axial. All the others are equatorial. And so structure B is the most stable chair conformer that you can form. Now let's repeat this process, if we can, but this time draw the two chair conformers for beta-D-glucopyranose. Well, you'll notice I will get the exact same ring structures. The only difference between the beta-D-glucopyranose and the alpha-D-glucopyranose is the chirality at the anomeric carbon. So if I draw my chair conformer, I get only this chirality as changing. Everything else stays the same. And again, I can draw two possible chair conformers. And so if I draw the ring flip structure, I end up with this. Okay, so we now have structures C and D. Now, which of the two conformers, C or D, is major? Well, if I look at structure C, all of the large groups, OHs and CH2Hs, are axial, and D, they're all equatorial. Having the large groups equatorial is energetically more favorable because it's less repulsive. So the most stable chair conformer for beta-D-glucopyranose is structure D. Now remember, beta-D-glucopyranose formed in 64% concentration in solution. Alpha-D-glucopyranose formed in 36% concentration in solution. And we ask the question, why? Well, you begin to see why. Energetically, compare structures B and D. In structure B, almost all of the large groups are equatorial except one OH. But in structure D, all of the large groups are equatorial. All the OHs and CH2OHs are equatorial. This is low energy. So if you are forming a chiral carbon and placing that OH in one of two possible positions, it will be energetically more favorable to put the OH up in the Haworth and form beta-D-glucopyranose because the equatorial position is lower energy than the axial. Remember, this conformation is the lowest energy of the two possible. So beta-D-glucopyranose predominates because it gives you a chair conformer that minimizes the repulsive forces by placing the OH equatorial. You should be able to explain this by drawing the chair conformers. Well, there you have it. We've taken our sugars quite a long way. We've gone from a straight chain Fischer projection to a cyclic Fischer projection, followed by a Haworth projection formula, which can be used to generate two chair conformers. Okay. Now those chair conformers indeed are the key to explaining why we get different percentage compositions when D-glucose cyclizes, and we get 64% beta-D-glucopyranose versus 36% alpha-D-glucopyranose. You should practice drawing the Haworths and the chair conformers, And you are responsible for being able to name any structure that's given to you, either in chair conformation, Haworth conformation, Fischer, cyclic Fischer. And to do that, you have to convert the structures back to the Fischer projection. Well, I'm Dr. Brian Lloyd. This is my Scribblecast. I thank you very much.